Chapter 3 of the Recurrent Neural Networks course. In this appendix, we show the global stability basic recurrent neural network and the details of derivation update laws. The presence of the linear term with a constant stable matrix in the basic recurrent neural network architecture is expressed in equation 3.16. The basic concepts are to have a bounded region for all trajectories. This guarantees that, for bounded input signals and bounded parameters, the internal state trajectories would not go unbounded but rather remain confined to, or converge to, a bounded region. As all parameters and trajectories are bounded, the convergence is then guaranteed. To pursue the stability analysis, we define the bounded vector m_t as equation 3.57. All components of this vector m_t are bounded by assumption. We also define the constant matrix A to be a stable matrix, that is, it has eigenvalues having moduli less than unity, in absolute value. For instance, A equals alpha times I, where I is the identity matrix and alpha ranges from 0 to 1, is a parameter. We then rewrite equation 3.16 as 3.58. For stability investigation of this now linear system, we choose the following general quadratic form as a candidate Lyapunov function, that is, equation 3.59. Note that a Lyapunov function is a scalar function that is used to analyze the stability of a dynamical system. A Lyapunov function must satisfy two conditions: it must be positive definite and it must have a negative definite derivative. If a Lyapunov function can be found for a dynamical system, then the stability of the system can be determined based on the behavior of the function. Specifically, if the function is decreasing along all trajectories of the system, then the system is stable. In equation 3.59, S is any symmetric positive definite matrix, and x*_1 is a center point that may be different from the origin. In Lyapunov theory, typically, x*_1 is chosen to be an equilibrium point of interest. In the present case, however, x*_1 is simply a point in the state space as a center to be determined. We note that this Lyapunov candidate is positive definite for all points with reference to the center point x*_1. Now, we calculate the difference equation of this Lyapunov function, as shown in equation 3.60. We use the dynamic equations, equation 3.58, into the equality EQ 3.60, and expand terms to obtain a quadratic equation in x_t. We can then reformulate equation 3.60 into the general quadratic form shown in equation 3.61. Where the square matrix G, the vector x*_2, and the scalar d bar are to be determined in terms of the known quantities in equation 3.60. A simple approach in determining these unknowns is to match the expanded equation terms, term by term, specifically, by expanding the expression on the right-hand side of equation 3.60, expanding the right-hand side off equation 3.61, and then equating corresponding terms in x_t, we can obtain equations 3.62, 3.63, and 3.64. Hence, for a given or chosen value of the symmetric matrix S, and the center vector value x*_1, the above equalities can provide a solution for a square matrix G, then the center vector x*_2, and then the scalar d bar used in the difference Lyapunov function. As a consequence, the difference Lyapunov function will become negative definite outside the ellipsoid defined by equation 3.61, with the left-hand side set to 0. Let us call this ellipsoid defined by equation 3.61, as ellipsoid B. Recall that a positive definite matrix has all positive eigenvalues and is associated with a convex function, while a negative definite matrix has all negative eigenvalues and is associated with a concave function. In graphical form, the ellipsoid centered about x*_1 is defined by the Lyapunov function in equation 3.59, must expand to include ellipsoid B. Thus, after expansion, we have another ellipsoid centered around the point x*_1, let us call it ellipsoid A. Ellipsoid A engulfs, or includes, ellipsoid B. Thus, outside of ellipsoid A, defined by the positive definite Lyapunov function, the difference Lyapunov function is strictly negative definite. Thus, by Lyapunov theory, all trajectories of this neural network for frozen parameters must remain in, or converge to, ellipsoid A. That is, the function is decreasing along all trajectories of the system. Thus it is stable. In other words, the global stability is established. To solve the set of equalities, 3.62, 2, 3.64, we choose S equals I, the identity matrix, the vector x**1 equals to 0, then equation 3.62 becomes equation 3.65. In equation 3.65, we choose the square matrix A to be stable, that is, it has moduli less than 1. By the singular value decomposition. Then, by the singular value decomposition, we have equation 3.66. Whereas a diagonal matrix of the square roots of the singular values of A and Q is the matrix formed of the corresponding orthogonal right singular vectors. Thus, by combining equations 3.65 and 3.66, we have equation 3.67 which provides a symmetric, positive definite matrix. Then to match equations 3.60 and 3.61, term by term, and from equations 3.63 and 3.64, we have equations 3.68, 3.69, and 3.70. By rewriting equation 3.69 to get the definition of x_2, we have equations 3.71, 3.72, and 3.73. Thus all terms are well defined in the difference equation, 3.61. Hence, we indeed found a Lyapunov function candidate centered around x*1 equals to 0, and it is described over an ellipsoidal region. Such region can be made to conservatively include the ellipsoid B around the point x*2 as defined above, where outside the bounded region defined by ellipsoid A, the difference Lyapunov equation along all the trajectories is negative definite. This ensures that all trajectories of the network will converge to ellipsoid A, thus establishing global stability. Finally, we remark that, in the training process of RNNs, the parameters are frozen over the finite horizon forward state dynamics and backward cost-state dynamics. This constitutes one iteration. The gradient descent update of the parameters occurs per one or many iterations, i.e., mini-batch, over the finite horizon training sequences. This constitutes a decoupling of the dynamics of the basic RNN and the parameter gradient updates during training. Thus, the global stability of the overall system is maintained. Finally, let us look at the details of update law's derivation. We now provide specific details of the architecture and its parameter updates. We assume the state initial condition x_0 is chosen, or given, as a constant, and thus the derivative of x_0 is 0. The split boundary conditions are then given in equation 3.74. Thus, the process is to use the initial state x_0, the input signal sequence s_t, and the corresponding desired sequence y_t to generate, forward in time, the internal state and output sequences. We define the final time loss function phi of z_n using the L2 norm squared, then we have equation 3.75. Where we define the output error by e_n equals to z_n minus y_n. Thus its derivative in equation 3.74 provides the final cost data shown in equation 3.77. As we have done before, the general loss function is expressed as a sum of separate loss function components as written in equation 3.78. Where the first term, the loss function Lt of z_t is defined by the L2 norm, squared, as shown in equation 3.79. Where we again defined the error signal e_t equals to z_t minus y_t, t ranges from 0 to n. We can now calculate the derivatives needed in the cost-state equation, 3.25, and in the gradient descent parameter update equations, 3.26, and 3.27, specialized to each parameter. For each parameter, the derivatives of all of them are given in equations 3.81 to 3.88. The parameter, weight and bias, updates in the output equation are now calculated. The regularization terms for all parameters contribute to equation 3.89. Finally, the gradient changes at each time step t for the linear output layer general parameters are shown in equation 3.90, which specializes to the specific two matrices and one vector as shown in equation 3.91, 3.92, and 3.93. Thus, the training process is to use the same initial state x_0, and the input signal sequence s_t and its corresponding desired sequence y_t2. 1. Perform the network time forward pass. 2. To use the boundary condition to perform the time backward pass. 3. Generate the gradient descent parameter changes. Then the update of parameters over the full sequence finite time horizon will steer the parameters along a approximate, stochastic gradient descent toward an acceptable good local minimum.